Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. We have been discussing about the IO subsystems in the previous lectures. We discussed the programmed IO and then the interrupt-driven IO. Although the interrupt-driven IO is better as compared to programmed IO, however, still both of these have a drawback. Namely, the CPU is involved actively and is participating in both cases. In the case of programmed IO, the constant loop and the status checking does not let the CPU just do something else. So in the case of programmed IO, the IO transfer speed is pretty fast. However, in the case of interrupt-driven IO, some other functions are being done by the CPU, and IO interaction takes place only when an interrupt is initiated. In the case of interrupt-driven IO, when an interrupt is invoked until the processor acknowledges after saving the environment, there is a lot of overhead. We have seen with the help of examples that the throughput would not be as the MIPS for a particular processor. Both of these techniques, programmed IO as well as the interrupt-driven IO, have two disadvantages. The first one, in all cases, CPU is involved and its ultimate speed or throughput is limited by the devices or the IO controllers which are connected in a particular computer system. So therefore, the speed of transfer from IO devices to the CPU would be limited by certain operations of waiting and, let us say, status checking. Now, the second problem in both cases would be that in one case, when we have a programmed IO, the IO transfer may be fast, but still in that case, we have the other activities are hampered. In the case of interrupt-driven IO, all activities go via CPU. So that means the data would be transferred to the registers of the CPU, from registers back to the IO. So the transfer involves CPU very actively. Now this brings us to a third mode of IO interaction, and that is called a direct memory access. Before we go into the details of direct memory access, conceptually the situation is simple. We say that we provide a direct path between IO and the memory subsystems. Now, you know that the system bus is involved. So in the case of the activity for what is called a direct memory access, the advantage would be that we will be able to isolate the CPU from the active transfer of data to and fro from the IO subsystems to the memory subsystems. Let us illustrate this motivation and the advantage of using the direct memory access with the help of a simple example. Let us look at the instruction load 2 with square brackets, comma 9 with square brackets. The symbols 2 and 9 represent memory locations. This particular instruction implies a transfer from one memory location to another memory location. However, this is illegal and is not available in the instruction set of the processor. If we want to implement this transfer, this has to be done in 2 steps. The first instruction would read load R1, 9 within square brackets. So we will load the contents of memory location 9 into register R1, and then followed by the store R1, within square brackets 2, the contents of R1 would be transferred to location 2. Thus, it is not possible to transfer from one memory location to another memory location without involving the CPU. The same applies to transfer between memory and peripherals connected to I/O ports. For example, out 6, data port is not possible, and the 2 instructions would be load R1 6, out R1 data port. Similar comments apply to the in instructions. With the help of these 2 examples, we see that the real cause of the problem is CPU itself. The transfer from I/O to memory or vice versa, in each case CPU acts as an unnecessary middleman. Also notice that the bus transfer is twice for each interaction with the memory and the I/O device. Now we could avoid this situation by direct memory access. So the motivation for providing direct memory access is that we avoid the CPU interacting for a particular transaction taking place between memory and I/O. By definition, we could consider the direct memory access as a mechanism by which the data could directly be transferred from I/O to memory, from memory to I/O, or from one I/O device to another I/O device. The advantage of using a DMA would be a better throughput, and the CPU time would be reduced. The unnecessary interaction of CPU with the I/O devices would not be there. The disadvantage in this case would be that we need some extra hardware. We need to have what is called a DMA controller, which may be a CPU in itself, or you could say it is an extra chip with the ability of interacting between different I/O devices or between I/O device and the memory subsystem. One could imagine that the DMA would take control of the bus. The situation would be as follows, that whenever we get a request for DMA to CPU, so CPU would have physically a pin where some request would come, and we could just say it is a request for bus or bus request. Now, this bus request would be treated just like an interrupt, and on receiving this bus request, just as in the case of interrupt, the CPU would store the environment, or it would continue running the present instruction and save the contents of all the registers which are involved in the present program, and then the control would be passed on to the DMA controller. The DMA controller would behave just as the processor. So it would be actively involved in the bus. So we could say that it behaves as a bus master. All the devices connected on a bus could be either master or slaves. By definition, a master would be a device which is able to initiate the addressing mechanism. It just places an address on the address bus, and then correspondingly the bus control is given to the DMA controller. Now, after the complete data has been transferred, then the control is given back to the CPU. Now, you can imagine that at one time only either CPU or DMA controller would have a control of the bus. Both of these cannot have control simultaneously, otherwise bus contention would take place. That means there would be a conflict for the bus, and the corresponding data on the data bus may not be valid or the correct data. The slide shows a typical interface that can perform the basic steps for a DMA operation. Notice a device becomes a bus master by asserting a bus request signal, and then it has to wait till the CPU acknowledges this bus request and then issues a corresponding signal. We call it as a bus grant signal. The handshaking is important. When bus request is initiated, correspondingly CPU grants the permission to DMA device in the form of having bus grant. If more than one DMA device is connected to the bus, a daisy chain arrangement could be implemented, much in the same way as we have discussed with reference to the interrupts. The arbitration for the bus would be required. The job of a DMA device would be then to transfer a block of data to or from the memory, and at the end of this transfer give the control of the bus back to CPU, and this would be done in the manner what we call the DMA protocol. The basic concept of DMA is simple, and it would provide a higher throughput. Direct connection would be provided between different IO devices and the memory. In that particular situation, if a common bus is being used, the CPU would not be able to utilize the bus during the time when transfer is taking place. It is important to see that a device has to be a bus master, and only one device would be a bus master at one time. The process of getting the control of the bus would be as follows. When a particular request for DMA comes or it is initiated by a device, and it would be indicated to the device whether it is a read or write operation, the CPU would complete the present status or present set of instructions, and at one point of time then it would pass on the control to the DMA controller by having the acknowledge signal, or what we said, the bus grant. The total data transfer could take place in two modes. In one case, we could say that after transferring every word of data, the control is requested again and again, but this would be less efficient. More efficient mechanism would be that the total block of data would also be indicated, and it would also be shown that what is the corresponding address in the memory from where the data is to be fetched, or if it is a write operation in the memory, then where the data from an IO device is to be placed. So therefore, this important information would be exchanged between DMA controller and the CPU. Let us look at the mechanism of what we call the DMA protocol. This is illustrated in the next slide. There are 3 steps involved in a DMA transfer. Firstly, the CPU sets up the DMA controller by supplying the identity or address of the device, the operation to be done, which means is it a read operation or a write operation, the corresponding memory address, that is the source or destination of data where the transfer is to be implemented, and the number of bytes required to be transferred. The second step would be the DMA starts the operation on the device, gets control of the bus through arbitration, and when the data becomes available either from the memory or from the device, it would transfer the data. The DMA controller supplies the memory address for the write or read operation. If the request requires more than one transfer on the bus, the DMA controller would generate the next memory address and would initiate the next transfer. This process would continue till whole of the block of data is transferred. There could be a number of DMA controllers connected to one bus. In such a situation, we could provide control to one of the DMA controller and allow a limited data to be exchanged. Many of the DMA controllers also have buffering mechanism. Through this buffering mechanism, we can provide flexibility and the delays could be reduced. The third step for DMA transfer would be that once the transfer is complete, the controller interrupts the processor, which then tells the processor that I'm done. DMA controller would just examine the memory and look at the entire operation for successful completion. Now there is an important point to be noticed. The DMA has a priority over interrupts. Now the question is, when DMA is activated and the transfer is taking place, then during this particular process the interrupt would not be entertained except for certain exceptions. That is, the internal interrupt may be entertained, or at the end of the transfer of data, the corresponding DMA protocol would indicate and it would release the bus grant signal. So therefore, the control would be given back to the CPU for the bus. Let us now look at different bus configurations which are possible for DMA implementation. There are 3 possible configurations. The first one is a single bus detached DMA. We have one system bus and the DMA controller is attached or connected to the system bus exactly the same way as a CPU is connected. So it would share the address lines, the data lines, and the control lines exactly as corresponding to the CPU. Now in this particular configuration, although it is very simple to implement, the throughput would be reduced. Imagine that a DMA controller is now behaving exactly the same way as the CPU was behaving. A DMA controller would now take the role of CPU. Whenever the transfer of data from IO to the memory is to be implemented, each particular data block would be passed on through the DMA, and DMA would become the bottleneck. Now, if we want to further increase the throughput, we could have an integrated IO and DMA operation. You can imagine that in this case, the controller would take the functions of IO as well as the processor. So this is shown in the next slide, and you could see from there that the connection, the interconnection from IO, one IO to another IO would be directly implemented without using the system bus. So therefore the system bus would be involved only for transfers to and from the memory. This concept could further be extended to a third configuration where we have two independent buses. One bus corresponds to the IO bus and the other one is the system bus. Now in this case, the DMA controller is connected on one side to the system bus and on the other side to the IO bus, and a number of IO devices could be connected to the IO bus. So this particular configuration would be easy to expand. It would have more flexibility. If we need to add up another IO device, we could do that simply by plugging on to the IO bus. Secondly, the system bus would also become free when the transfer is only required from one IO to another IO. Only when transfer from memory or from IO device to memory is required, only then the system bus would be utilized. Let us look at these three configurations in the next slide. The first slide shows the mechanism for single bus detached DMA. As explained, the DMA controller in this case acts as a replacement of the CPU and utilizes programmed IO to exchange data between memory and an IO module through the DMA protocol, which we have already explained. This particular configuration, while it is very cheap and is clearly less efficient, we will see that with CPU controlled programmed IO, each transfer of word consumes 2 bus cycles, and therefore the throughput would straight away be reduced to half. The next slide shows the single bus integrated DMA/IO. Now you see in this example that 2 IOs are connected to one DMA module or DMA controller. The DMA logic may actually be a part of the IO module, or it may be a separate module that controls one or more IO modules. This concept can be taken one step further, and you see a number of IO modules could be connected to a DMA module by using an independent IO bus, which is indicated in the third slide. This reduces the number of IO interfaces in the DMA controller to only one and provides an easy expandable configuration. All of these cases which we have discussed, that is the three configurations, the system bus that the DMA control shares with the CPU and memory is used for DMA transfers. Therefore, when exchange of data between memory and IO is involved, the system bus would be utilized. For the sake of comparison and looking into how the DMA implementation would improve the performance, we are going to look at two simple examples with the help of some numerical figures with or without DMA operation being implemented. These two examples would be illustrated in the next slide. Let us look at an example where an IO device transfers data at a rate of 10 megabytes per second over a 100 megabyte per second bus. The data is transferred in 4 kilobyte blocks. If the processor operates at a clock frequency of 500 megahertz and it takes a total of 5,000 cycles to handle each DMA request, let us find out the fraction of CPU time in handling the data transfer with and without DMA. For this example, if DMA is not used, then IO can transfer data at a maximum rate of 10 megabytes per second, whereas the bus capability or bus throughput is 100 megabytes per second. So simply 10 divided by 100 corresponds to 0.1, which means 10% of the CPU time. Now we are just assuming that the IO device is active all the time. So therefore, in practice, if the data provided by IO is lesser, then the corresponding CPU activity would be lesser. However, this is 10% is the maximum value for the case when DMA is not used. Let us look at the solution for the DMA being used in the next slide. With DMA, the time required in handling each DMA request is 5,000 cycles. Since 2.5K DMA requests would be issued, so therefore the total time taken would be 5,000 multiplied by 2,500, which is 12.5 megacycles. Since the CPU clock is 500 megahertz, we divide 12.5 by 500. The corresponding time spent would be 2.5% of the CPU time. This example illustrates that using DMA is a better option and the CPU time would be 2.5% instead of 10%. In both cases, we have assumed the 100% activity of the IO device, which may not actually be the case. Let us look at another example where we explicitly deal with the overheads as well. We have a hard drive with a maximum transfer rate of 1 megabyte per second. It is connected to a 32-bit CPU with a performance figure of 10 MIPS, that is 10 mega instructions per second. The clock frequency is 100 megahertz. Assume that the IO interface is DMA and it takes 500 clock cycles for the CPU to set up the DMA controller. Also assume that the interrupt handling process at the end of the DMA transfer takes another 300 CPU clock cycles. If the data transfer is done using 2 kilobyte blocks, calculate the percentage of the CPU time consumed in handling the hard drive. Let us look at the solution. Since the hard drive transfers at 1 megabyte per second and each block size is 2 kilobytes, there are 1000 divided by 2, which is 500 blocks transferred per second. Every DMA transfer uses 500 plus 300, that is 800 CPU cycles. 300 is at the end where the interrupt would give back or grant release signal would be given to the CPU. So the total overhead would be 800 CPU cycles. This gives us 800 multiplied by 500, which is 400,000 cycles per second. For a CPU clock of 100 megahertz, this corresponds to 400 into 10 raised power 3 divided by 100 into 10 to the power 6, which is only 0.4%. Again, in this example, we have assumed the 100% activity from the hard disk. If the data to be transferred is less, the CPU time would be lesser than what has been calculated. This is a maximum value just to illustrate. We also have made another example that there is only one DMA device. That means there is only one hard disk taking part in the activity. At the same time, we assumed that the CPU would grant the DMA the control of the bus as soon as it just requests. However, the CPU may already be actively using the memory, and that may take some time before the grant is given to the DMA controller. So therefore, some sort of additional wait state might be incorporated. So therefore, the problems could be extended to having more than one DMA device on the bus and then the corresponding time sharing between CPU and DMA controller. The DMA controller needs to take control of the bus in order to transfer data to and from memory. For this purpose, the DMA controller has to have the bus, and this would be available only when the CPU doesn't need it. This could be implemented by temporarily suspending the CPU activity. This technique is called cycle stealing. This concept is indicated in the slide. Notice that for a complete instruction cycle, there are only specific points where the control of the bus could be accessed, and that is just before fetching the new operand or data from the memory. The cycle stealing effectively retards the performance of CPU and places the CPU in a wait state. Now notice that there is a difference between giving a control to the bus by cycle stealing and by implementing an interrupt. In the case of an interrupt situation, the environment needs to be saved, whereas in the case of cycle stealing, the environment is not saved. Just you could say that the process is, the CPU is halted and control of bus is given to the DMA controller, and after a few bus cycles or maybe one bus cycle, the control of the bus is given back to the CPU. For having short transfers of data, this cycle stealing could be quite effective. we have noticed that in DMA control, still the DMA controller is playing a lot of role, and connected with the system bus, it interacts with the IO devices exactly in the same way as the CPU. We could go one step further and make the IO controllers more intelligent. And by making more intelligent, these IO controllers could behave like CPUs. And therefore, we could say that the functionality of DMA control is integrated with the IO's interface. This concept of IO channels or IO processors just delegates more functionality to the IO interface. In this case, the program corresponding to IO is stored at some location either in the main memory or in the IO processor. In some books, the IO channel refers to having only a CPU in the IO interface, whereas the IO processor is a complete processor along with the memory provided in the IO interface, and the IO function transfer in the form of DMA could take place straight away by executing this particular program, either from the main memory or from the memory corresponding to the IO processor. Let us look at this concept of IO channels and processors in the next slide. The simplest form with which we started with IO interface was that CPU directly controls the peripheral device. This we called microprocessor controlled device. Next, we went on to the concept of IO controller under programmed IO. We further expanded to the concepts of interrupt, and now we have said that the DMA is executed by using an intelligent IO. Now this IO channel could further be implemented as shown in the slide in two different ways. A selector channel controls multiple high-speed devices and at any one time is dedicated to transfer the data with one of these devices. Therefore, the IO channel selects one device and therefore executes transfer of data. Each device or a small set of devices is handled by the controller or the IO module. For a multiplexer channel, the IO is handled with multiple devices by having a multiplexing. This could be a byte multiplexing or it could be a bit multiplexing. For example, the resultant character stream from 3 low input devices with different rates and different individual streams could be as A1, A2, A3, A4, then B1, B2, B3, B4, and so on. And after multiplexing with these 3 inputs, we will get A1, B1, C1, and so on for the low speed devices. For the case of high speed devices, we could have a block multiplexers that interleaves blocks of data from different devices. Let us look at another important problem. By providing DMA, we have provided control of the memory to 2 devices, to CPU and to the DMA controller. Now, I hope you remember from previous lectures that in the case of memory hierarchy, we have a cache between main memory and the CPU, and also the concept of virtual memory organized in the form of pages from the secondary memory and the main memory. Now, a number of questions would arise. First of all, we have virtual addresses and physical addresses. So therefore, how do we coordinate the activities of accessing the same memory by two different devices? Through this sharing of the memory by DMA and the CPU, one needs to organize the software and the hardware activities. One simple solution could be that we could use the virtual addresses for the DMA as well. This would mean additional translation. Just as the CPU was translating the virtual addresses to physical addresses, then DMA would doing the same thing. This would increase the overhead and the effective throughput would decrease. There could be some other ways to organize the interaction between memory, CPU, and DMA. This is illustrated in the next slide. The first initiative by using virtual addresses instead of physical addresses for DMA would mean additional overheads. The major problem with DMA with regard to physical addresses is that a transfer cannot easily cross a page boundary. In case an IO request crosses a particular page boundary, then the memory locations to which it was being transferred would not be contiguous in the physical memory. Because of this reason, the memory locations would correspond to multiple virtual pages. Each of this page would be mapped to another physical page. Consequently, if we use physical addresses, we must constrain all DMA transfers to stay within a particular page. One method to allow the system is to use the virtual addresses. That is, DMA would also work on the virtual addresses. In such a system, the DMA unit has a small number of map entries that provide virtual to physical translation. The operating system provides a mapping mechanism initiated by IO. Using this mapping, the DMA unit need not worry about the location of virtual pages involved in the transfer. There could be a second technique which could be utilized, and operating system would break the DMA transfers into a series of smaller blocks. Therefore, a single physical page would be transferring the data within the same page, and sub-blocks could be chained together. Now, if this is done through software, it would mean that operating system needs to coordinate the activities. The same thing could be implemented through hardware. Another important factor to be kept in mind is that DMA control is provided to the virtual memory or the physical memory. Now, in the case of address translation, if we do not have a write-back mechanism, there could be two copies of the same data. Once DMA has written a data and that is not updated in the cache, in that particular situation, the inconsistent data would be available. So therefore, this particular aspect has to be looked into. The best possible way would be to provide the access for DMA to the virtual memory. As suggested, the routing of the I/O activity through the cache ensures the consistency of data. This, however, is expensive and potentially has a large negative performance impact on the overall system. Since the I/O data is rarely used immediately and may therefore displace useful data that may be required for the program running in the CPU. There could be another choice. This is to have the operating system selectively invalidate the cache for I/O read and write, or force write back to occur for an I/O write. This is often called cache flushing. This particular approach has no drawback as far as hardware is concerned. Probably it is more efficient if the software can perform the function. This flushing could be done also through hardware mechanism for selectively flushing the invalid cache entries. There are a couple of clarifications which are required with reference to some of the terms that we have been using. We have been using serial and parallel transmission. Keep in mind that within the CPU, the transfer of data is always in parallel form. When we talk of serial transmission or a parallel transmission, this is with respect to I/O interface or I/O peripherals. That is, the data from the I/O controller up to the peripheral could be transmitted in the form of a parallel stream through, for example, a ribbon cable for the case of a printer, or by using simply a twisted pair. That would correspond to serial and parallel transmission. Now we have been using the term simplex and duplex. Simplex implies data transfer in one direction, whereas in the case of a duplex situation, the data is transmitted simultaneously in both directions. As an example, if we have a modem in our computer connected to internet, this situation is for a duplex link. Now, in certain situations, we could have half duplex where the same medium or the transmission medium supports bidirectional transmission, but one at a time. So, at one time in one particular direction. Now we have been talking about the programmed I/O, the interrupt-driven I/O, and the direct memory access. All these terms are with reference to the CPU. So CPU is controlling the activity, whether we have the direct transfer or interrupt-driven transfer or a programmed I/O transfer. So this would refer to CPU. Now to wind up today, what we have talked about, we just started with the motivation for DMA. We discussed why DMA is required, what is the functionality of DMA, what are virtues of a bus controller or a bus master. The control of bus is given through a particular protocol, and then we went into the configurations, different configurations of the bus implementation. In nutshell, we could gradually go from programmed I/O to interrupt-driven I/O and to DMA, and finally we discussed the processors and channels integrated into the I/O together. So this would make the I/O interface more intelligent and delegate the power from CPU onto the processors within the I/O controller. And that is probably one of the best technique that could be followed for a DMA access. With that, we close up the chapter corresponding to the I/O subsystems. That's all for today. Till next time, Allah Hafiz.